So in this video, I'm going to walk you through step by step how to use Newton's second law using linear momentum in order to generate the equation of motion for a particle, specifically of a system that has 1 degree of freedom. And this is all in the worked sample problems, which I highly suggest that you look through or follow along with as I'm doing this, because in there I wrote down at least my approach to solving equations for the equations of motion. So I kind of tried to write down the exact steps that I'm taking. Of course, the order in which you may do things, it might be different for you, but at least this gives you somewhat of a guide for how to go through this procedure. So we'll start with this, the very first example, which is you have a particle P that's rolling on along a that is not a semicircle, semicircular. I mean, that's also not a circle, but it's a little better. Semicircular surface. And this particle P has a mass of m. And you're going to assume that there's no friction between the particle and the surface. And the goal is to find the equation of motion for P. And as a side goal, we're also going to find the angle at which P separates from the surface. But first, let's focus on this objective here, again, which is to find the equation of motion for point P. So of course, we're going to start by defining our reference frame. So here we have our fixed frame, so fixed here, A1 and A2. And P can roll around the surface, so it makes sense to define a moving reference frame B, so B1 and B2. So it's going to point in this direction here, and we know that this radius is r. So the first thing I would do when I'm solving for the equations of motion is to write down the degrees of freedom of this system, because it's going to tell you how many equations of motion you need. And so you may have heard I keep saying find the equation of motion, and that's because the degrees of freedom of the system are equal to 1. And I also, just for my own sanity, I write down what is the coordinate that we're using for that degree of freedom, right? Which in this case, it's going to be theta, right? It's this angle here that's going to be changing or varying with time. So I write down, we've got 1 degree of freedom, and I'll just spell this out here, and our coordinate is theta. And that's because when we, you will see shortly, when we we're going to end up with a bunch of equations, and when we're choosing an equation or ultimately deciding on what our equation of motion is, that equation of motion should be in terms of your coordinate and its derivatives, right? So it's just important to write that down. And so the next step is to draw a free body diagram for particle P, right? So this is, again, going back to statics. So this was step 1, and so step 2. Okay, so we have a particle P. That particle has a mass, right? So we know that there's going to be a force acting on it in this direction equal to mass times gravity. And then because it's in contact with the surface here, a normal force is going to be applied onto particle P. And this is our free body diagram. So again, step 2, draw your free body diagram. Step 3 is take that free body diagram and actually write out the force vector that's acting upon the particle P. So we're going to now write from our diagram the force vector that's acting upon particle P. And so we have here, of course, F of P. So this vector here, due to gravity, force due to gravity, is acting, again, if we look back into our reference frame, it's acting in the negative A2 direction. So we're going to write mg A2 minus. And if you look at the normal force vector here, this is it's acting, if we go back up to our original problem here, it's acting in this direction, which you can write in terms of B1. So we can just simply write NB1. And so now we have our equation for force applied. And so the next step is to, for those of you who thought you'd be sad that kinematics is going away, it's not. This is where we're going to write now the acceleration of particle P in a fixed frame A, so A, P. And hopefully you might start to see now with our steps that we're taking the advantage of the supermagic formula. You don't have to go through calculating velocity. You can just write acceleration because that's ultimately what we want. So we can use our supermagic formula. So we have the acceleration of point P in frame A. And so we have our first term here is the acceleration of point O in frame A, because point O is the origin of B, plus the acceleration of point P in frame B, plus 2 times the angular velocity of frame B in frame A crossed with velocity of point B in frame B, plus angular acceleration of frame B in frame A crossed with our position vector ROP, plus again our angular velocity crossed with angular velocity crossed with our OP. Those, parentheses there. So the acceleration of O in frame A is 0. The acceleration of point P in frame B is also 0. And here we have our 2 times theta dot B3. It's positive because theta is moving in that direction. Cross with the velocity of point B in frame B, which is also 0. So now we have our angular acceleration crossed with ROP, which is just equal to RB1, plus theta dot B3 crossed with theta dot B3 crossed with RB1. And so now, again, this is the old stuff, just simplifying here. All of these terms go away, so what we're left with is R theta double dot B2 plus theta dot B3, and here we have R theta dot B2, and finally we get to R theta double dot B2 plus R theta dot squared, and then this ends up being a negative B1. And next we're going to use Newton's second law to equate force and acceleration. So use Newton's second law which is that force is equal to mass times acceleration. So we plug in our forces. So we have force vectors equal to negative mg a2 plus nb1, right? So that comes from right here, equal to m times our acceleration vector, which is up here. So now we have r theta double dot b2 minus r theta dot squared b1. All right, so now I've just cleared the space. We're going to continue on. I'm going to write out our equation again. So we have negative mg a2 plus nb1 is equal to m r theta double dot b2 minus m r theta dot squared b1. So our next step, step 6, is to rewrite this equation where all the terms are in the same frame. So you'll notice as you're looking at that equation above, we have an A2, a B1, a B2, B1, and we need everything to be in the same frame. We're written in terms of the same unit vectors. It doesn't matter what unit vectors you want, so you could write this all in frame. You could change B1, B2 into terms of A1 and A2, or you could take that A2 term and write that in terms of B1 and B2. We're going to do the latter just because it's the simplest, right? There's just the least amount of A terms. So to do this, recall that we have written the relationship. So this, I think, is in week 2 notes. The relationship between the A1 unit vectors and A1 and A2 unit vectors and the B1 and B2 unit vectors. So here we're going to write out the relationship so we can go from, we can plug in A2 and get it in terms of B1 and B2. Of course, you could also write this the other way where you have the B1, B2 terms on this side and you'll have the A1 and A2 terms where I'm writing B1 and B2 here. It's just a different matrix in between. But again, that's all in your week 2 notes. And so this is the relationship between A1 and A2 and B1 and B2 written in matrix form. We can now write this out. We only need A2, so I'm going to write out the equation. So to get that, I multiplied this term by this term. So I have sine of theta B1 plus, and then I multiplied these two terms here, so plus cosine theta B2. And now I plug this in here. So I can now write that as negative mg sine theta b1 plus cosine theta b2 plus nb1 equals mr theta double dot b2 minus mr theta dot squared b1. And then I can distribute this term, this negative mg term out, so I am left with negative mg sine theta b1 minus mg cosine theta b2 plus nb1, and then that's equal to the following. All right. And so now we are ready for step 7. So step 7, we're going to equate B1 and B2 terms separately. This is what I mean for that. So first we're going to gather all our B1 terms. So B1, 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 and then we have here our B2 and B2. So for our B1 terms, we can write negative mg sine theta b1 plus n b1, and then we have that the terms on the left-hand side are equal to the b1 term on the right-hand side, which is negative mr theta dot squared b1. And you might notice that I can simplify this relation by simply getting rid of these b1s, right? Because I can just, they cancel each other out. So I'm just going to quickly rewrite this without the b1s to be plus n equal to negative mr theta dot squared. And I'm actually going to keep doing this. I'll probably only by mistake ever actually write out the b1 or b2 in the future, but I wanted you to know, why those disappear. And then we have our b2 terms. So again, on the left-hand side of that equation, we have negative mg cosine theta, and on the right side we have mr theta double dot. See, only by accident. Okay, and so now we have two equations, and if you recall back to our requirements, so the very first question, right, was to write down that we needed that we had a 1 degree of freedom system, so we needed one equation of motion, and then our coordinate was theta, so we needed that equation of motion to only contain unknowns that were theta and its derivatives, so theta, theta dot, theta double dot. And it turns out that you can actually just simply take this equation here. Oops, I hit those double dots. And this equation here satisfies what we need. The equation above, while it does have a theta term and a theta dot term, it also has this n term here, which is unknown. So we can use this equation here, and this is our equation of motion for the system. So just let me write it again up here. So our equation of motion is equal to negative mg cosine theta equal to mr theta double dot. Of course, we can simplify a little bit, and by convention we try to put all of the theta dot and theta terms on the left hand side of the equation. So this turns into r theta double dot plus g cosine of theta equals 0. And so this is our equation of motion. And when we solve this equation of motion or simulate, essentially what we're looking for is we're looking for theta, or the values of theta, that if you plugged in theta and you plugged in its double derivative, right, that this equation would hold true and that you'd ultimately get 0. So that's what we mean when we say solve the equation of motion. We're like, what is the theta value? Again, that if you, or theta values, that if you plugged it in here, it would satisfy, if you also consider its double derivative, it would satisfy this equation. Okay, so this is it. We did it. First equation of motion, first of many in this class and in your career as a mechanical engineer. And if this isn't the first, well, we'll just pretend it is. And so you might be asking, all right, like, what about like this equation here, right? We got two equations, and so sometimes that happens. You get more equations than what you need, right? We had one unknown, so we only needed one equation, but that doesn't mean that this other equation isn't useful. And in fact, as I mentioned in the beginning, a secondary goal or secondary of this problem was to also find at what angle the particle, so again, if we just draw out a little schematic here, that the particle separates from the surface, right? So at some point, this particle is going to be traveling along and it will no longer be in contact. And so what is that theta value, which that happens? And you can actually use this equation to find that. So when the particle is separated from the surface, n is equal to 0. So we can again take this equation here and we can set n equal to 0. So now we have negative mg sine theta equal to negative mr theta dot squared. Cross out those m's. And now we just call here, this is theta sep. This is the separation angle. And then it's equal to negative r theta dot squared. So even though it's a leftover equation, it still can be helpful for us. But again, in terms of what our ultimate goal was, it was this, right? Derive that equation of motion, and here it is. So in the next example, I'm going to show you, we're going to go through the exact same steps, and we're going to solve for the equations of motion because we now will work with a 2 degree of freedom example.